All right, good afternoon, everybody, and thank you for being here for this special joint RAL M cubed and EOL seminar. No offense meant towards CISL, HAO, and ACOM for not including them in this, but I'm pleased to introduce today XIAOMIN CHEN, who is an assistant professor at the Department of Atmospheric and Earth Science at the University of Alabama in Huntsville. And there he has built an impressively vibrant team doing research in hurricanes, and it's a place he's been since late 2022. So his history goes back to Nanjing University, where he got his PhD in 2015, where he also got his bachelor's as well. His interest in the weather goes back to his childhood, however. He was curious about tornadoes and severe weather from elementary school, and so his passion continued to carry him through into doing some significant research. Prior to coming to University of Alabama Huntsville, he has spent some time at NOAA's Hurricane Research Division in Miami. And this includes a National Research Council postdoc fellowship, but there he did a lot of great work, and that launched his career into his university position. So between NOAA, his PhD, and at University of Alabama, he's already produced a very strong and impactful publication record in a number of areas of tropical cyclones. His research focuses on modeling dynamics and observations, and those include boundary layer processes, near surface winds during hurricane landfalls, and he's done a lot of great work with large-eddy simulations to improve forecast models such as NOAA's HAFS model at NOAA. But he's also done very significant work in rapid intensification, sheared cyclone dynamics, and eye-wall dynamics. And among his recent honors is the 2026 AMS Banner Miller Award for developing a high wind boundary layer parameterization scheme with advances in intensity, including rapid intensification, and forecast skill of NOAA's operational hurricane forecast model, HAFS. So here at NCAR, he has almost become an honorary member of NCAR as well. He has many fruitful collaborations here throughout his career, including working with George Bryan at M Cubed and others in M Cubed. There he's helped build and test new capabilities of CM1. He's worked with EOL quite a bit in observational aspects of hurricane boundary layers, and more recently with RAL in understanding hurricane boundary layers in landfalling storms. So we're very happy to have him here today. Please join me in welcoming Dr. Chen, who will talk to us about his recent research.
Thank you, Chris, and thanks everyone. Good afternoon, and it's an honor to bring the three labs together in the seminar title, so I feel very honored. And I was studying the hurricane for over 10 years so far, and today I'm going to address the topic. I was curious for many years, like how to better estimate surface wind during hurricane landfall. So I'm using ERES and also using radar analysis. Part of that work have been done by my students, Zeb Leffler here. If you have any questions, you can ping him to address that. And I acknowledge all of my co-authors, collaborators over the past few years contributing to this project, because we really need a lot of knowledge combining modeling and observation together. So, all right, let's continue about that. So I've starting from Melissa last year, and this is landfall wind hazards in the Black River regions. So I don't have the total number about the damage caused and the fatalities, but so far, at least you can see, if we can reliably estimate or predicting the surface wind over land, especially in the coastal region, that would be very helpful for the situational awareness and also for the risk communications. So because I don't have the digits about that, so I switched that to Helene. At least we have NHC status here. The wind hazards alone, causing the direct fatalities, 65. That just tied the records back to the years of 1963. So it's very remarkable. And when we see the 12 hours before Helene's landfall, we check about NHC's warning area, tropical storm force warning area, the blue, and of course, strongest wind near the coast, that's with the hurricane force wind radii. But the thing is, this warning area was based on the 1 minute sustained winds, right? And specifically, NIC defined hurricane intensity based on the 1 minute sustained wind at a standard height, 10 meters above the ground, above the sea level. And do we have a lot of data over land? Yeah, we do. But we don't have the direct 1 minute sustained winds for the ASOS network. Yeah, we have quite a few. Some of them are losing power quickly after landfall because of wind damage. Either you broken the power infrastructure or you just destroy the facility here. And another thing is we can convert that sustained wind to 1 minute sustained winds by applying the gas factor based on the Harper's technical report in the WMO. But somehow we have another mobile tower by the UF folks here, and they have FCMP tower. Yeah, you can deploy to the ideal location, potentially when the landfall Iowa location. Potentially we can grab the peak winds there. So they can have high frequency measurements, so that can be converted to the 1 minute sustained winds. But we only have very few tower, the mobile towers. That's also very expensive to maintain. Another thing to supplement to this network will be the weather flow. Yeah, it has 1 minute sustained winds, that's great, but it can be anywhere. This example was on the rooftop, it's not standard height, it's still affected by the wind. If you want to get 10 meter winds, you may need some magic to interpolate the winds to the 10 meter heights. So anyway, we have some data, but it's not enough, unfortunately. And particularly the heterogeneous land surface were complicated, especially the ASOS data, wind measurements. So I'll give you an example of things like rapid weakening after landfall. Yeah, everyone knows we have frictions, we dissipate quickly after landfall, typically, right? But one gap here, if you watch this intensity evolution before landfall, yeah, the vertical line here is the landfall time. Before landfall, you have so many data that can help you have the best track data all the way up, right, to the major hurricanes. But immediately after landfall, the rate shading box here, you only have just a few surface station data here. And you can obviously see the best track data over this few hours here can be quite higher than the surface observations. So the question here is how we can actually estimate surface wind during landfall, particularly in the coastal region where you have the strongest winds, right? So the one powerful relationship we use over the ocean, open ocean, is using the drop zone composites. So they bring the drop zone data based on the wind speed. So you have the high scale here using the log scale. So if you see the wind increases linearly with height, that's basically the log wind profile. And the ray line here will be the reference for log wind profile. So you see in a high wind situation, like a 60 meter per second surface wind, you have a 100 meters about log layer depths. And this log layer can become gradually deeper to a few hundred meters in the weak wind situations. This is a powerful relationship. Why? Because you don't always have the surface wind measurements, like SFMR, like Focus yesterday, we talked about that. SFMR has been discontinued. We don't have the direct surface wind measurements of the ocean. Yeah, we just need to rely on some new instrument to fill in that gap there. So, but the log law, if you know the wind above the surface, so this is the log law equations, frictional velocity here divided by the constant, von Kallen constant, 0.4. Now belonging Z, the data of the observations, and Z now will be surface roughness. So if you have the wind data, for example, at 500 meters, and we can literally get the 10 meter winds if we know the surface roughness. So how we do that? So we insert the wind data 500 and 10 meter height into the equations and divide the equation 2 by 1. So now the 10 meter height will be the function of 500 meter winds. Yeah, that's something we can observe. At least not the surface, right? It's much easier to observe than 10 meter winds. And then the only thing I'll know is the surface roughness. Yeah, over the ocean, that's the sea state. Yeah, so you can actually derive that. And so that's the kind of relationship we have. But things become complicated over land because log layer won't be single log layer assumption will be challenged. Why? Because you have internal boundary quickly develops in response to the abrupt change of surface roughness. So the surface roughness can be changed a factor of 10 to 100, even more, from water to land. So because of the enhanced surface frictions, yeah, the wind above the internal boundary kind of have the memory of the ocean, so it's remain log scale. But within the internal boundary, that can have a kink in the wind profile, and then have a transition all the way to be response to the new surface roughness here. And within this kind of shallow internal boundary, you also have a fully adjusted layer. Yeah, within this shallow layer, you can have another log scale near the surface, but that can be very, very shallow. Yeah, ZEP has a Doppler radar analysis that generally below 100 meters. So the issue over the land right now is we don't have the IBL development, the profiling measurements about the winds too much. one thing is, yeah, of course, you need to get like a field profiling system in a coastal region, in a field campaign, but we don't have like official field campaign over land for the hurricane landfall, unfortunately. So many decades, and so we don't have a fully understanding how the IBL developed over land, and so this is one challenge here. Yeah, but somehow, like, because we don't have a better approach, yeah, when we estimate surface wind over land during hurricane landfalls, especially in the coastal region, yeah, we rely on the mobile radar or ADD radar, project the wind to the surface to generate surface wind. We hope that's the truth, but that's kind of very challenging because single log layer obviously has been challenging here. It does not hold anymore. So, but motivated by this, so today our question, yeah, special part one here, like we try to understand how the near surface wind evolve in the coastal region during landfall. Yeah, I just fully try to understand how deep the fully adjusted layer, like log layer, going to be within IBL, because that's very important. If you know the fully adjusted layer depths, if you know the wind measurements at that level, you can interpolate that all the way to the surface. And the second part is how we best estimate surface winds using observations. Yeah, because we don't have the profiling system for the IBL, the one way we try to fill in that gap is generate the data. So generate the truth. So hopefully the areas, yeah, that's the like quoted truth. Using areas like very fine resolution grids, hopefully we resolve all the structure here. And that's a new framework developed like for TC landfall, like particularly first time using by the Chris 2023 paper. Okay, so this is the idea. And particularly we run the large-eddy simulation under the realistic hurricane conditions. And what do I mean realistic? So basically we try first to derive the drop zone composites of the hurricanes, the mature hurricanes. And then we have tangential wind, the radial wind, and potential temperature and mixing ratio structure here. So previously in 2021, and George and I have worked on the small patchy areas framework. So in that framework, because that's simplified framework, we have assumptions. Assumption basically assume like radial gradient of radial winds is much larger than the vertical gradient of vertical winds. And that's not valid in the IWO region, so that's why this framework is mostly applicable outside the IWO. So then we just push the boundary there. We have the 45-meter situation here, so that get the profile data at this location when the surface wind 45 meters per second. So what do we need for this framework? We need gradient wind, capital V here, and the location about the 45 meters per second, and the radial gradient of gradient wind. Lapse rate can come directly from here at about 5 Kelvin per kilometers, and the humidity, relative humidity here is 80%. So this is what we have. Okay, so the areas domains are channel-like, riding along the coast, 12 kilometers each over water and land. Yeah, this distance has been considerably selected because typically previous observation studies say the IBO, like PBO transition from water to land can be complete, nearly complete, within 12 kilometers inland. So that's try to cover that. And we have 20-meter resolutions for 3 directions. Because this is like ocean to land, we need open boundary conditions on the eastern boundary here. So then we need 80 recycling over the open water here, try to put the 80 back here so we can generate the steady state very quickly. And regarding about the SST, it's 2 degrees warmer than a 2-meter temperature, the best on the buoy dale like Joseon showed before. And over land is 2 degrees cooler compared to the 2-meter air temperature. Yeah, because previous modeling study or even observation show there's a sensible heat flux is negative in the coastal region. Yeah, that makes sense because you have precipitation and overcast before landfall, so that can make a land cooler than the air. Okay, so another thing is like we're choosing 3 different, we're choosing a thermodynamic nudging over the ocean subdomain. That's an interesting setting here. We're using that for the 2021 paper. So using the nudging, then you can prescribe the, you can generate the profile of turbulence and winds under realistic thermodynamic conditions. That can make more realistic data. Yeah, one kind of like major conclusion from that study. So we just adopt that in this framework. And we have 3 different land types. As you can see, we're using homogeneous. Yeah, that's really beautiful because that really simplified the explanation of the results. If you're heterogeneous, there's a lot of complication when you see the wind data there. So we have 3 different land types, and from 0.2, 0.4, all the way to 0.8 in the urban area. So basically, we want to see how the IBL developed over a different land surface type. And we also want to see how robust our proposed approach to estimate 10-meter winds, whether it's robust for different land surface. So we have a 2 hours simulation. We get a steady state, so we get like 2 to 3 hours like composite structure on the next slide here. So we can see the internal boundary development over land. And on the right, when the x-axis here is positive, that's over ocean. Yeah, inland will be negative. Okay, so the wind speed, full wind speed composite structure shown in the upper level panel here. The jet were about around like 700 to 800 meters. Okay, so we're using the log scale for this plot because we want to see how dramatic change for the surface wind here. So it's from 45 meter per second over the ocean. Yeah, quickly, that's category 2. Quickly displaced become tropical storm force, like 20 to 30 meter per second. And we have IBL developed, coastal region, of course, have convergence zone, you have updraft, and IBL developed quickly from a few tens meters and to become like 400 to 500 meters here. So this is a very beautifully captured by the empirical equation by Stuart in 1988. So we're using the alpha is a constant, is a coefficient tunable like 0.28. Yeah, that's the consistent with his like a textbook here. So this IBL height will be a function of distance inland, that'll be the x here. And you can also see the net will also be proportional to the surface roughness because this is power of 1 here, this is negative 0.8, so it's gonna be like proportional to the roughness. That's to say if you have a higher land surface roughness, you can slightly have a deeper IBL height. Yeah, that's what we entail from this equation. But anyway, so for the TKE structure on the bottom here, yeah, that actually can show the IBL even better, right? Because this is typically when the layer, when the TKE was respond quickly to the new land surface roughness from water to land. So the maximum PKE over the water is near 20 meter per second, meter square per second square, but you're gonna be doubled quickly after landfall because the friction has significantly changed over land. So that will induce a lot of shear production of TKE near the surface here. So that's what the results tells you. And this kind of like IBL development can be shown in earlier observational study with mobile radars. That's a Hurricane Francis 2004. So this is a kind of SR, smart R radar we deploy in the Florida coast here. The Barrow Island was here. Onshore flow is generally easterly flow here. And we have the red box just encapsulate the RHI scan from radar. Basically, that's the radar radial velocity scan. Yeah, that's the different two different times. So we have 2 slices here. And clearly over the Barrow Island, actually, you can see there's IBL developed quickly above that. So it's very shallow at the beginning, but it can develop with distance inland. So that depth is very comparable to what we showed earlier. But anyway, this is only have like a long beam wind, unless you have a Doppler analysis. The Doppler analysis, you will miss the surface level data. So it's really hard to attempt, satisfy all the needs we have. We don't have the full winds here. So anyway, based on the previous composite results, now we can extrapolate different vertical wind profile at different distance. Yeah, we're starting from the ocean, 1 kilometer east of the coastline. The black line here, you have like quasi-log scale, like about 500 meters below the jet level. Only just 1 kilometer inland, so the near surface log layer become 50 meters. And then this has become gradually deepens. 6 kilometers, the log layer become 200 meters or so. And to 11 kilometers, when the transition is nearly complete, it's about 400 meters. Yeah, this is very close to the jet, and consistent with the previous Doppler radar analysis, say the IBL transition nearly complete within 12 kilometer transition zone. Okay, so this is just one experiment. You may ask me, okay, what about the other experiments? So I try to compare the different experiment on the same plot right now. So every panel shows the different distance inland, and every different line here will be the 3 experiments. So the red line, red line is very strikingly different here, right? That's the urban area. So you have more friction. So not surprisingly, for every distance inland, the red line always to the left. That's going to mean the wind was weaker. So friction is stronger there. Decelerate the wind more significantly. And also the IBL high, if you see here, was slightly deeper. That's consistent with the Stuart's equation as we discussed earlier. Okay, so this is the kind of the takeaway here. Yeah, IBL high increased slightly with greater surface roughness, and same distance, IBL wind remains weaker for the higher surface roughness. All right, the next question is how are we going to estimate the coastal 10-meter winds using observations? I'm trying to starting from the radiosondes because that's very typical for the landfall missions. It's very hard to release a lot, because the high wind, the balloon is not very stable. That in the areas, we don't have that problem. So we just release virtual sounds as close to 1 kilometer inland. So it's pretty safe, right? So in the model, you got the freedom. So that's the beauty of freedom as well. So we release 100 sounds at 1, 3, 6, and 9 kilometers. Yeah, along this black line here is just every 20 meters you have radio sound release. We integrate that so with the 3-dimensional winds, And meanwhile, we know their blue sound, they have like 5 meters per second winds based on the National Weather Service documentations. So that would be superimposed on the three-dimensional winds, will be affecting these sounds downstream. Yeah, we release that from 10-meter height. That would be the bottom model levels, and integrate forward for 200 seconds, or reaching the 1 kilometers, or leaving the domain. Yeah, because the domain is not that very large. So then I give an example about the 1 kilometer, 100 sounds here on the left panel here. Yeah, there's a lot of profile. If you see, for example, the radial sound profile from the lateral view, you actually, for example, the 1 kilometer, the solid line here, the blue will be the minimum 10 meter sustained winds, at that location. 1 kilometer inland. The blue will be, radial will be the maximum. So I just illustrate what the radial sound really measure in the real hurricane conditions. So if you have a weak winds here, so the vertical profile of this sound will be more vertical near the releasing side, right? So you just sample the environment near releasing side. But if you get like stronger winds here, you can just affect it immediately downstream. So as you're rising along, so the radial sound wind profile is kind of a composite of different turbulent winds, particularly turbulent winds at different locations downstream with different height. So I'm trying to mapping these two sounds, the solid line on the left panel here. So interestingly, you can see the wind difference about 50 meters is as large as 30 meters per second, just based on two different sounds. Yeah, is that exaggerating? I'm gonna show you, probably it's not. So I would have the sounds from Sim Iverson kindly providing me this plot. So in the Hurricane Simon 2014, they released the two rapid sounds fire, like sequence, like only 1 second apart, they released two sounds. All right, so you have a different pairs here, but just pay attention to these two pairs, for example. This is like green line and the black line here. So the trajectory ends when they splash over the water, right? So the splash distance can be as large as 8 to 9 kilometers. And typically like drop sound splash time is 5 minutes. So that's 300 seconds. So if you do some simple math, they give you the difference about the velocity about 30 meters per second. So just very similar to what we showed in the earlier time. So so that's just to show how large variability the sound profile can give you. So so that's one thing we really learned from this area's experiment. All right, so with this area's wind profile data, like different heights, now we perform like a log fit equations, basically still a log equation, but I just rederive that to be a function of the log in z, the height coordinates here, gonna be the function of wind speed. So the slope here will be the k divided by the frictional velocity. So that basically, with this data, different levels, you can have a linear feet here, actually can produce the slope, also produce intercept, that'll be the surface roughness. So once you get the slope and intercept, and assign the z to be 10 meters, you can get the 10-meter winds. So this is how we can do that. So the orange line here basically is a log wind like projection here, all the way to 10 meters. So the issue is like we cannot possibly deploy like or release 100 sounds simultaneously like in the coastal region, like especially 1 kilometer inland. That's the coastal flooding region. Nobody wanted to stay there. So the more realistic number based on the previous literature review is about 3 or 4 sounds. Even that probably apart by a few minutes. Okay, so we do the 100,000 random sampling of 4 sounds out of the 100. So based on that, we can generate a PDF about the errors. What the error? So error basically the log fitted 10-meter winds minus the areas produced is like the surface wind at the release site. So with that, we actually can generate the arrows here, or U10 bias. So from the blue to orange to yellow here, that's the log feed with different depths. So you gradually increase the feeding depth from 200 to all the way to 500 for the yellow, the whisker and bar plot here. But I actually even just focus about the medium arrow here. It's still like 10 to 15 meters per second. So it's pretty large weak bias using the sounds here, right? So this is a 3-panel here, show the different experiment. So I have a different distance inlands as a function of the x-axis here. But generally that's pretty robust. Another like a purple whisker bar plot here, that will be the log projection. We don't using the wind profile at different levels. We're just using the winds, 4 sounds wind near the 500 meters. And using that to project the surface 10-meter winds. as long as we know the surface roughness. But surface roughness, we know that, right? That's a different land surface is prescribed by the RES, is 0.4 or 0.2 or 0.8. So we actually can compute in that. So actually this one, not too bad. The medium error is within 5 meters per second, and you have just positive bias a little bit. So the key takeaway here, yeah, you have a log feed about 4 sounds per file. Yeah, it not potentially can get a very accurate surface wind. The weak bias is notice that. And log projection 500 meters sound mean wind to the surface, yeah, produce reasonably better results compared to the first one. And why is that? The log projection works well, at least slightly better than the previous one. Yeah, first thing is 500-meter winds. Yeah, during the coastal transition is not affected. The IBL is still shallow and not approaching the 500 meters to 700 meters yet. And then another key takeaway is the surface wind from water to land. The 80 to 95% of wind reduction only happens within 1 kilometer distance. So that basically say you have 3, 6, and 9 projection. The further downstream, the wind reduction is not that significant compared to this rapid transition zone there. Yeah. So this is another reason, I guess, why the log projection, just using one level data, slightly work better than the entire wind profile. But anyways, this is a kind of the conclusion for the part 1. How does near surface wind evolve over land? And as we find, yeah, nascent IBL deepens inland with a new log layer forming in its fully adjusted region. And the depths can vary for a few tens meters all the way to 300 to 400 meters within the coastal region. And if you have higher surface roughness, you have a slighter, deeper IBL, and by the weaker winds consistently inland. That's sustained winds. So then how better estimate overland 10-meter wind using observations that are using the radiosonde here. Yeah, we find radiosondes is sampling about different turbulent winds. Yeah, you just cannot use that to treat it, okay, we can use that to define hurricane intensity. No, it's turbulent wind. So we cannot do that. And log feeding can introduce substantial low bias in 10-meter wind. Yeah, about like 10 meter to 15 meter per second. Yeah, log projection slightly did better. But this is kind of like it's the part 1. The part 2, when we try to talk about radars, so like I think EOL folks were like that even more compared to radiosondes. So we try to provide the radar analysis first and follow up by the synergy between the radar and AOSPRE, the radar simulator. We try to understanding how our approach method work in reality. So back to this plot again, yeah, just don't get tired about that. We have a new line I haven't introduced so far. That's a gray dashed line here. That's the domain average. It's subdomain average, land subdomain average, wind profile. So basically this is a temporal average as well, right? So you get like the domain average and temporal average. So you can have like the wind profile kind of average between the 6 to 11 kilometer wind profile. You actually can capture the log wind profile within this range here. So that's very encouraging because the VAD, the velocity azimuth display, is using a similar idea. It's kind of like temporal and spatial average, right? You get a wind profile. Imagine you have like a sweep, Doppler sweep here, and you have like a different elevation. You have a conical surface here, and then along the conical surface, you have a different ring corresponding to different heights, right? And you get to go up, so you have like wind profile about the general environments here. So they generally get the Weber number 0 component at a different ring, so you get a wind profile here. So hopefully this areas at least give you some sense. Maybe the VAD can capture the IBL structure. But this is confusing, right? And then the literature suggested, okay, previous literature, they're study the hurricanes, landfall hurricanes for, yeah, there are quite a few cases from 2000 all the way to 2012. And they're using log feed of VAD wind profile below 300 meters or the jet, whichever is lower. And they find a strong low bias, yeah, to be 10 to 30 meters per second. And then they concluded that a log is not appropriate methodology to use to estimate the surface wind in the TCBL. So I'm trying to understand a bit more about that. So I just checked some earlier studies using the VAD analysis. So you can identify, so this is kind of composite, but generally for the previous VAD analysis, you can have like only one data below 100 meters typically, and a vertical resolution about 60 or something like that. So it's kind of relatively coarse compared to the IBL depths, right? IBL sometimes is less than 100. So if you have that resolution, you typically observe one data or probably even no data. So to address that, and my student Zeb have published a paper in 2025, a GR paper. He analyzed the 2 landfall hurricanes, Ida and Zeta. So he refined the PyArt package. So now they have including new features. They including the range control. Yeah, basically have a prescribed area where the wind can be retrieved and have additional QC to make sure you won't be affected too much by the noises. And also fixing the balanced feeding window in the vertical direction. That's it is to say, if you have VAD winds, you have a balanced window central on that height. Yeah, you cannot bias to either side about that window. So this is some like new features. And then we have vertical resolution using 20 meters. Yeah, this is with the purpose to better capture the IBL structure. And the VAD domain here, we're using 8 kilometers after testing. Yeah, using a slightly large domain, the result does not change too much. Okay, so this is the results just for this particular moment for the IDA and zeta. And the black line is a VAD profile. And we also have the log law feet between the 200 to 600. Yeah, you do have log there above the internal boundary layer. Yeah, but if you ignore the 1 or 2 data below that, so you do the log law feet, you probably have the projection all the way to the surface, the 10-meter height. Compared to the SL station, like 10-meter sustained wind, you're going to have a very large weak bias, right? So this is a kind of something like probably explain why the Cooper mentioned that the log layer projection does not work because VAD don't really have too much data in IBL. All right, what if we're using the IBL data, just the bottom VAD height, and using the log law projection, which is upstream surface roughness. And now you have better match to the surface 10-meter sustained winds. Yeah, this is one movement. You definitely can question me whether this is robust, right? So we tested that for the entire, a few hours for both storms during the landfall period before they reach an IO or just the outer rain band region. So this is the method 1. Yeah, this is the method 1 we talked about earlier. This is a log law feed using a different wind profile and feeding all the way to the surface. And surprisingly, we find similar big arrows here. That's a weak bias. Yeah, 10 to 20 meters per second, constantly for the 2 cases. If you're just using the log law feed, ignore the IBL separately. And then if we're using the log law projection of a 500-meter wind, we're just using 500 meters long and project that to the surface. And now we have a much smaller bias, but it becomes positive this time. Yeah, the focus on black line first, because black line using the HRD's surface roughness in the upstream quadrant. So now like a 5 meters per second like arrow here, right? So that's kind of very similar to what we showed earlier in the dropsonde or radiosonde 500-meter projection to the surface. You also have like a 5 meters per second positive bias. But then we have another 2 lines. So the purpose of another 2 lines, because we know the land surface is heterogeneous, right? You have a minimum surface roughness, so you have a large one, the HRD kind of like a composite, the medium one. So we have the minimum open space here, 0.03, based on using the NOAA CCAP, and we have 1.2, that's urban area using CCAP, and we're using that to give you the uncertainty, like how large the uncertainty of your results or the bias results here will be sensitive to the selection of upstream surface roughness. So the uncertainty here from minimum to maximum here is about like 10 meters per second, yeah, for both cases. So it's still like a kind of be a little large. So the last one will be the one we propose using IBL VAD winds. Yeah, now we project the wind from the VAD bottom height is about like 80 meters, something like that. So now the orange line using the HRD surface roughness, you can see it's kind of very approaching the 0 meter per second, like bias here. And you have also the uncertainty here from minimum to maximum surface roughness upstream. Yeah, the uncertainty generally less than 5 meters per second. This is kind of very encouraging. So basically, this is just to show you like leveraging the IBL winds, the radar retrieve IBL wind, can potentially accurately estimate surface wind. And all right, so to this point, you may ask whether the job is already finished. So it's still not. And why is that? I give you an example about Hurricane Ida. So this is the CCAP land cover. Yeah, you can see this is the easterly winds here during this analysis period. Yeah, you can find the urban area on the upstream and become the open exposure near the radar and SL station site, right? But the problem is like, yeah, you have different significant land surface heterogeneity. Like how are you gonna interpret the results? Is that gonna be really robust? This is something we don't know. Another one you can always question about whether the VAD, which is domain average winds, is that fair to compare with 1 point-wise surface wind measurements? Yeah, we try to testing this in the next using model. Yeah, and synergy between the model areas and the radar simulator. So first thing we do, yeah, we try to using homogeneous heterogeneous land surface conditions, as we did in the RAS experiment. So that crosses out the second factor. So now we can focus entirely on the first factor, the domain average wind vs pointwise winds. So within the V80 domain, having an ASL station nearby the radar in the center, yeah, we have a 20-meter resolution, right? So we have over 31,000 ASL station, virtual ASL station, can be used in this domain. That allows us for a systematic assessment about the V80, especially the V80 wind projection against the surface measurements, which is provided by the ARIAS itself within the V80 domain. So we do that by extracting the radar safe radio data from the large-eddy simulations. Yeah, so yeah, this is thanks to like Ting Yu and Brad, and also the Kim Manning about very helpful discussion about that. So we get some results from last year, and so we put the radar at different locations, 3, 6, and 9 kilometers. You can see the V80 domain is very small because we have very narrow channel here, but still we can get the wind profile all the way to 600 meters using the 2-kilometer domain here, 2-kilometer radius. All right, this will give you an example about how the radar data was captured by the AOSPRE. So we have like a VCP212 pattern. You actually can see some boundary strict structure there captured by the radars. Yeah, radar can see some like boundary coherent structure here. So radar height is 20 meter above the ground level, spin width 1 degree just to try to match the 880 radar. And within 1 hertz areas restart output after 2 hours, and this cycle complete within 3.5 minutes. Yeah, using that, we can apply the V80 package again, because that's exactly mimic the 880 radar. So now we're using the similar PyR package V80 analysis and 20-meter resolutions. And what do we compare here is log-log projection using 60 meters within IBL. Another one is a 500 meter above the ground level, typically above the IBL based on the previous analysis. So then what we can do here is project the wind to the surface, right? The observation, yeah, this is something we know from the V80. And then we try to project that to the surface. The surface roughness, as I mentioned earlier, is provided by the area settings. That's a 0.2 or 0.4 or 0.8 roughness length. And project that to the surface, U10 projection, and compare to the 10-minute sustained winds at a 10-meter height. That's ASL station measurements, the virtual ASL station measurements. Yeah, I didn't explain why using 10 minutes so far. But as a hurricane scientist, it will be interesting to show that first, I guess. Yeah, so I using the 4 hertz area's high frequency output. Yeah, why not actually using 1 minute sustained winds to define hurricane intensity, but I just want to show you visually what that means. So this is the coastal region on the east, and the western part will be the land. Yeah, you see this is like a linear structure along the onshore wind flow directions. Yeah, that's the boundary streaks or like coherent structure near the surface. You have a high speed and low speed fluid parallel each other along the mean wind directions. So the 1 minute sustained wind, you can capture these structures. So in other words, 1 minute sustained wind is kind of like a gust. You have the turbulent component inside. So if you do the PDF about the peak to the PDF, so it's kind of Gaussian distribution anyway, but the central part of the PDF curve is a 45, right? That's our setup, perfect. But the range from minimum to maximum can be over 10 meters per second. Yeah, so you actually have this uncertainty in our 1 minute sustained winds. So what the chance we can get the peak wind there? Second one, using 2 minutes, U10, that's ASL station measurements. And for the China Meteorology Administration, they're using 2 minutes to define the typhoon intensity. So this becomes smaller than 1 minute, but it's still, you can see the coherent structure here, right? Over the ocean or land. The range is less reduced, but it's still like 7 to 10 meters per second. Still have a large uncertainty. But once using 10 minutes, yeah, it becomes much cleaner, right? So over the ocean is clean, like 3 meters per second. The minimum to maximum over land, yeah, acceptable. Along the medium value here, it's a 2.5 meters per second on each side. So again, the log-law projection and log-law assumption, you have assumed the flow is a quasi-stationary. So this is the flow we can use. The 1 minute sustained wind is still very fluctuate. Yeah, it's not the steady state. So that's why I'm compare that to the 10 minute sustained winds. With that said, now we do try to show the area's 10 minute sustained wind profile within the V80 domain. And I show that as a dashed line here. And a different experiment show 3 different panels. And there are different lines here will be the black 3 kilometers, green to be 6, and red to be 9. Yeah, of course, go further inland, your IBO were getting deeper, right? So that's just a show earlier. And then we perform the VAD analysis, as I said earlier. I grab the OSPRE, grab the CF radio, we can perform the VAD analysis. The solid line will be the VAD analysis. Yeah, this is just to demonstrate. Yeah, we radar sample the volume of the turbulent flow as well. It's instantaneous wind composites, literally. But within this VAD analysis, you still can capture quite a well about the general domain average wind profile using the VAD. So if you focus about the 60 meter height winds, the difference compared to the domain average is less than 1 meter per second. So this is very encouraging. And then we try to project to the surface to get the log projection, get the surface winds. So then we have, remember we have over 31,000 virtual SL stations. So now we can have the whisker and bar plot about the SL station measure winds here. And this is a 0.2, 0.4, 0.8 will be different colors. You have urban area, yeah, you have a different distance inland. You always have the weaker winds here, especially for the medium value. So now let's focus about the 500 meter VAD projection using the radar retrieve 500 meter winds, project that to 10 meter. So then we actually find the black dots here. It's very close to the peak 10 meter sustained wind over land. It's about 1.5. And once you use the power about the 60 meter VAD projection, yeah, we hope they can produce better results, but actually it's not. You have a positive bias here within the 6 kilometer inland. Yeah, I'm trying to figure out why that happens. So 2 to 3 meter per second. It's not significant, but it's larger. Because right now the hope is we can capture the median values, because median value were more representative of the mean wind of the environments. So then we'll try to go back to this equation again, the log law projection, right? So we mentioned earlier 60 meter winds within 1 meter per second of the truth. So the only thing that can mess up this surface wind estimates will be the surface roughness used in these equations. Yeah, I just provide them with area settings, 0.2, 0.4, or 0.8. But once we do the log law feet over the wind profile in IBO here, we actually find the for the black line to all the way to the red line here, the fit of the surface roughness is a factor of 2 or 3 times greater than the reality. It's consistent for 3 experiments here. So basically, that's the effective surface roughness will be greater than the actual land surface roughness. Yeah, it's not surprising because recent year, like Japanese typhoon scientists also find some recent result. The GMA, they tune their surface roughness to higher values to have a better surface wind estimates. Yeah, so that's the one issue. So why is that? Like, I think about that. I guess this inflated surface roughness is because the inner layer or the internal boundary layer is trying to match the flow, the outer flow or the flow above the internal boundary with the remain impact. They try to match the adjusted wind profile above. So the slope here still makes sense, right? The smaller slope here, that's going to mean the friction velocity was larger. That's kind of the slope log law feet here. And once you go inland, the wind weakens, so you actually have a steeper slope here. But the intercept, the surface roughness will be the intercept. You have the same slope, but the intercept can be moved around to matching the wind above. I guess that's what happens here. All right, so with that, what we can do, and we use an inflated surface roughness and a VAD wind at 60 meters. Now we have like orange star here. It matches pretty well with median value for all the PDF, yeah, different distance here. So that's very encouraging. So what that can be used for? So I just want to remind, like when we talk about wind damage, as I showed earlier, wind damage is not caused by the 1 minute sustained wind. It's more direct relevant to 3-second gust. So with this methodology, we can get a median value or a true sustained mean wind, and we multiply the gas factor. Then we hope we get the peak 3-second gust over land. That'll be very useful for the wind hazards predictions. Yeah. All right, summarize for this part 2 here is with sufficient vertical resolution, the VAD analysis from the 880 radar can resolve domain average IBO wind profile in the coastal region during landfall. And compared to the traditional methods, leveraging the radar retrieve IBO winds, yeah, provide you a better chance to have more accurate surface wind estimation, particularly using the inflated surface roughness. And this can be useful for the wind gust prediction in the future. And in future tests, like I think Zep can do that, right? So we can incorporate the fast scanning radars like over the heterogeneous land surface. And for the 880 particularly, that's the rough to smooth transition. So instead of like from ocean, water to land, that's the most rough. So that can be another setup. We can test in this methodology in the future as well. Anyway, this is my research part, and I will talk about briefly about future research on wind hazards. Yeah, this is the Monday on Colorado. Yeah, thanks, Chris, to leading this successful chase about this storm here. You actually have almost a dust storm near the surface here. Yeah, it's very high wind situations. Yeah, so what make me interested about the wind hazard for hurricanes is not just like it blow everything when a hurricane was landfall. Sometimes you see something like that, very narrow wind damage swaths. Yeah, if you're using the car there as 1.8 or 6 feet as reference, yeah, that damage swath is like 15 to 20 cars width. Give you about 30 to 40 meter localized wind damage. Yeah, just eastern of that, you see the roof is remain fully intact. Yeah, so why this happens? Yeah, so another fact about this extreme wind gust here is happening about F3, that's the Wakimoto in black. 1994, this is believed the first time the surface wind speed has been assumed as high as F3 for landfall hurricanes. Just keep in mind the EF scale is not introduced by that time, so that's why using F3. And that distance was within 12 kilometer inland. Yeah, what a coincidence, right? We're using 12 kilometers. So then I think this data for Hertz output over the 10 minutes can be really useful to explain why this localized wind damage happens. Yeah, as I mentioned, over the ocean, the sustained wind 45, right? But the peak wind here is approaching 60. So over land, you can pay attention to this kind of orange cascadings. You have many survivors of the high winds. They sometimes even intensify inland. It's almost everywhere, like prevalent in the coastal region. So using this data, yeah, we have a publication right now under review. So hopefully that can be published in the future. So try to address why this happens. So another part is this framework does not applicable to the IWOL, right? So we have a sub-kilometer WRF simulation recently, and we focus about this finger-like echoes along the IWOL interface. They are associated with the peak wind gust, sustained winds, yeah, outside of this, yeah, there's a missile vortices here, and peak wind will be typically radial outward. Yeah, that's a conceptual model we have proposed in the recent publications. So basically, based on the dynamic diagnostics, and we find this extreme wind, this yellow shading here, radial outward of this mesoscale 80s, is because of the amplified eddy circulations. Yeah, the eddy circulation intensification is because of radial advection terms and also the pressure gradient force. So they accelerate the wind, so it's not the downdraft. We don't find that the downdraft play a significant role here, but rather the RADV and pressure gradient force play a role. So how robust this is in the 40 large-eddy simulation work, yeah, that's something we can fully address in the future. So I think, yeah, so we're using Sanchez Gomez, like this is a plot provided by Eric, yeah. Using this method and then provide the forcing term, generate the inner core areas. This is wind swaths, by the way, at 25 meters, and we can literally try to get the wind swaths. We can have the high frequency output, try to diagnose something, complement the earlier area studies. Because before we talked about the areas outside the IWOL, right? In the IWOL, you have extra dynamics here. So using this data, we hopefully can have a better insight to explain the full why sometimes localized damage happens in the IWOL. Can that be different outside the IWOL? Yeah, based on the dynamics in the corner flow region here, it potentially can be. So that's something we can do in the future. Okay, I have 10 minutes left, so I will try to stop here and take any question. Thank you.
Thank you for that great talk. I just want to pause to mention that we do have people online. Please use Slido, and we'll be happy to take questions both online and in person here in the audience. So questions here. All right.
Hi, really interesting talk, James Pinto from RAL. I was curious why you think the internal boundary layer depth doesn't really change much as a function of the surface roughness length that you were looking at, and also kind of a corollary to that is like how different is the depth of the IBL over the ocean compared to when it makes landfall, after it makes landfall?
You said IBL over the ocean?
Yeah, the IBL over the ocean, is that pretty shallow?
Yeah, IBL, yeah, I mean, the surface roughness change over the ocean is very small. Like
Yeah.
they are like 0.0.
I guess maybe not the IBL, but just the boundary layer over the ocean.
Yeah, boundary elevation, yeah. They don't change that much. Like, this is kind of like a very focused area, like just onshore flow landfall here. Yeah, why I say it's not changed that much, like this is kind of empirical equation used by Stoll, like, because it's like a power of 0.2 of surface roughness here. So that's why it's not changed that much, but it's slightly deeper as well. You have roughness here, right? But you also have roughness here, the negative 0.8. So that give you the power of 0.2. So give you like slightly impact, but not that dominant impact here. Does that address your question?
Yeah, kind of, but I was more curious, like from the simulations point of view. I mean, that's kind of an empirical relationship, but you would think that there'd be more enhanced turbulence. Well, you see that the TK is a lot stronger.
Yeah.
With the higher roughness, but why doesn't that like generate a deeper IBL?
I guess that's something related to about the peak TK region there. That's relevant to the fully adjusted layer. So the IBL on the top is kind of connected to the ambient. So it's probably two different scale there. Yeah, fully adjusted layer compared to the IBL top. Because IBL top there have still some portion of the wind profile connecting to the wind is not affected above. Mm-hmm. Yeah, I guess that's probably why. But fully adjusted layer, yeah, it's just going to deepen. Yeah, deepens with distance inland. So.
Okay. Thank you.
Yeah.
Just quickly related to that, can you remind us, like, if there's strong model sensitivity in CM1 to the SGS settings for this particular setup?
Yes. Yeah, I think Miguel is here. So we testing the MBS scheme. This is like the default SGS scheme here, just the TKE. We also tried MBA, like nonlinear backscattering scheme, like that reduced the TKE quite a lot. Yeah. So this is like a 45 or like even higher. To that, like we reduce like 30% or so. Because I think they have additional forcing about near surface wind. That changes the sheer production of TKE there. Yeah, they have a sensitivity there. Yeah, we can all say this is just the truth. Yeah, I just wish we have more observation to indicate how really strong the TKE is over land. Yeah, but we don't see too much data so far.
We have a question online by Chris Cruz. Are these eyewall mesoscale eddies due to some vortex instabilities? Or are they associated with embedded convection in the eyewall? Good question.
That's a good question. And in this paper, we try to allude to like some kind of a barotropic instability. But we cannot say that's the dominant factor here because you also have a counter flow. You have an inflection point from both radial and tangential wind. So to some extent, I think that's kind of like three-dimensional instability here. But why this is happening during the middle to late stage of RI. So when you have developed the rain profile, so that actually relevant to the barotropic instability as well. So we don't find the exact like explanation based on that but we find the tendencies kind of it's similar. So we cannot say exactly what's going on right now because it can be three factors together. Yeah, that's some future work. Definitely we need to quantify, potentially using idealized models.
Questions? Oh, sorry, okay.
Thank you. Great talk. I had a question about the internal boundary layer. So you showed the simulations, but they're like unidirectional. So it's like more of a. But in the cyclones, they are rotating as well. So you have.
Yeah.
So the flow is, and the storm is moving as well. So it's 12 kilometers from the coastline in those simulations, but in reality the flow is moving radially as well. So I don't know how are you planning to investigate like not just the streamwise evolution, but more including rotation as well? And yeah,
that's something going to be done by the full RES. For the simple patch one, like we're using 12 kilometers, basically that's 1 or 2 grids inland. Yeah, mesoscale grids inland. So that's our try to focus on based on that kind of a tiny scale near the coastal regions. Yeah, what do you say? All right, you have curvature. So I guess that's because right now we don't focus on the inner core regions mostly, right? Because we cannot do that for this simple patch areas approach. So for the future, we'll do the full inner core. Yeah, that can be better captured. When you're outside inner core, the curvature is slightly smaller compared to the inner core region. Mm-hmm. So that impact can be less compared to the inner core region. But that's a good point. Yes.
And a quick follow-up.
Yeah.
So you also show simulations over 2 or 3 hours, but in reality, the storm is moving over those 2 to 3 hours. So
yes.
is there like do you think there might be a shallower boundary layer that is not fully developed because of the storm's movement, or do you comment on that?
Yeah, that's a good point. I cannot answer you right now because I don't know what exactly the inner core past that and how they're gonna move. Like to this, we get a steady state. Like, yeah, I know people say there's no steady state in hurricanes. That's true. But here we try to get like a fundamental level understanding. Yeah, if it's not moving, what exactly we get, right? That's just the starting point. I fully agree with you. Like we need to consider about moving. Yeah, so the full areas is something like we can be done in the future. Yeah.
Hi, Xiaoming. Very interesting talk. I'm curious about the radiosondes part. Traditionally, the Weather Service and researchers use like 200 grams balloons or something like that because we want to hit the tropopause.
Mm-hmm.
But for your case, you're interested only in the boundary layer. So I'm curious if you had made any assumptions about like balloon properties, like weight and whatnot, to see if, like, for example, can we get away with more but smaller balloons, for example?
Oh, yeah, that's a good point. I mean, if you use a small balloon, I guess the rising speed here will be different. Yeah, for this, I using the typical, like, for the National Weather Service station, they release the large balloons. So the documentation give me 5 meters per second. For small balloon, I don't have data. If I know what the rising speed going to be, like, yeah, that can be superimposed onto this, like, advection scheme here.
Okay. During PRECIP, we use 100-gram balloons, so at least we have that data, but there were no typhoons.
Okay. Yeah.
Thank you.
Yeah.
Right. Sorry.
I had a question about the 6 kilometer domain, right? And it's just recycled and it's fed into the larger domain.
6 kilometer domain.
Yeah, in your LES simulation, you had a 6 kilometer domain, and if I'm understanding, you do a recycling technique before you actually advect it into the big domain. I was wondering, right, because this is mostly, I mean, I have no doubt that this is quasi-neutral, if not almost neutral. Is there buoyancy in here? I thought maybe you mentioned that there was buoyancy.
It's a nearly neutral stability.
Yeah.
Yeah, it's have a lot of surface fluxes, but shear will keep that neutral.
Well, that's what I was just saying. Yeah.
Yeah.
So we have a 6 kilometer domain though in the surface layer. Your winds are ripping, so you're going to get these longitudinal structures that form, and I don't think your 6 kilometer domain is going to be large enough to resolve them. So they're going to see each other infinitely. They've shown this a lot of times in near neutral situations.
Which 6 kilometer domain you mentioning about? Like, is it 12?
The recycling domain.
Oh no, recycling I just get a patch here. So recycling we have a 6 degrees actually. Recycling I capture the winds about like 2 kilometers east of the coastline here, and put that turbulent information back to here. Yeah, we don't have 6 kilometer, recycling domain.
I thought from the image that you were showing, I thought it was a 6 kilometer domain.
Oh,
okay. Interesting. Oh, then I thought that would be a problem because you showed the streaks, and I was thinking about the advection of potential longitudinal streaks that are just seeing each other over and over and over at that wind speed, and you just advected them in there.
Yeah.
And right, they're real, but is your LES able to resolve them is a whole other question. Is it just something that's propagating in? Mm-hmm. Anyway, cool. Really cool study.
Yeah, thanks.
Yeah, I want to come back to the question here on the radiosondes that Rosie asked. I think it just left. But the one issue with real radiosondes is that there is a long smoothing on the winds, especially in the boundary layer. So like 20-second runnings average to get winds to filter out the pendulum of the radiosonde under the balloon. So with real radiosondes, that might be a little tricky to replicate this. However, if you could probably get away with that and say, we don't use an unwinder, we put the radiosonde directly underneath the balloon, which is operationally not done, then maybe this could be done.
Mm-hmm. You say the radiosonde under the balloon?
Yeah, so, I mean, typically there's 30-meter string between the balloon and the radiosonde. And so there's a lot of pendulum effect, and that gets filtered out in the wind calculations. So in the lowest 100 meters, you smear out the entire profile.
Okay.
But technically, it's possible to skip the rope and just put the radiosonde directly underneath the balloon. the price you pay for that, you mess up all your measurements, temperature and humidity. That you lose. That's why it's not done.
Yeah, that makes sense. Yeah, I realized that there's a additional filter about the wind. Yeah, they don't just produce a raw turbulent wind at each grids. They have some filter there. I know that.
Yes, it's extremely, I mean, especially after launch in the lowest 200 meters or so, there's a lot of pendulum because of the launch.
Oh, okay. Yeah. Yeah, that probably may complicate the results here.
Yeah.
Yeah, okay. That's a good point.
Thank you all for being here. I just want to say quickly that XIAOMIN's here through Friday morning, but especially today and tomorrow. So if you want to talk to him, he's in RAL FL2. Happy to help set you up a meeting time with him. Anyway, thank you for the wonderful talk. Let's thank our speaker again.